Dear students, welcome to this third lecture on unit number 5 centrifugal pumps of our subject turbo machines. In this we shall see the velocity triangles and the work done by the centrifugal pump on the liquid being handled by the pump. So the velocity triangles and work done by a centrifugal pump on the liquid that is handled by the centrifugal pump. The expression for work done or the energy supplied by the impeller of a centrifugal pump on the liquid flowing through it may be derived in the same way as we did for the expression of a reaction turbine, the reaction water turbine. Figure shows one vane of a partial impeller, right? So this is the partial impeller shown here, and one vane is drawn. So this is one vane, right? The liquid enters the impeller at its center, and the liquid leaves at the outer periphery of the impeller. So this is the inner periphery of a impeller, that is also called as eye of the impeller, center of impeller, and this one shows the outer periphery of the impeller, right? So we have some assumptions. The following assumptions are made to simplify the mathematical analysis. Okay, assumption number 1, liquid enters the impeller eye in a radial direction, in a purely radial direction. It means what? The whirl component of the velocity of water at the inlet is neglected. So VW1, whirl component of velocity of water at inlet, VW1 is neglected, is 0, and the flow component at inlet, that is VF1, equals the absolute velocity V1 at the inlet. So VF1 is equal to V1. So logically alpha is equal to 90 degree. You can see over here the vane is shown which has some curvature, and the rotation of impeller is shown in an anti-clockwise sense. Okay. The water is assumed to enter radially at the inlet tip of a vane. So therefore VR1 velocity is drawn tangential to the vane at the inlet tip of a vane. This is the tangent drawn to the impeller at the inlet tip of a vane. VR1 velocity vector is tangential to the vane at the inlet tip. Okay. Then U1 velocity, that is the peripheral velocity of the vane, is drawn with arrow on the left hand side, because the rotation of impeller is anti-clockwise. So it is the peripheral vane velocity at the inlet tip, U1. Okay. So draw this like this, joining the starting point of U1 with the end point of VR1 gives you absolute velocity V1 at the inlet. Okay. Further here VW1 is neglected, whirl velocity at inlet is neglected. So logically V1 is along the radius, right? V1 is along the radius, that is shown, and the VF1 component of velocity at the inlet will be equal to V1. So therefore alpha angle that correspond to V1 velocity will be equal to 90 degree. VR1 velocity makes an angle theta with the tangent drawn to the impeller at the inlet tip. Okay. Similarly at the outlet, the VR2 velocity vector is drawn tangential to the vane, making an angle phi with the tangent drawn to the impeller at the outlet of the vane, right? Then we draw U2 velocity. u2 is the vane velocity at the outlet of the vane, and the impeller has anticlockwise rotation, so u2 velocity is drawn in left direction. Okay, the end point of u2 here is connected with starting point of vr1, and this gives you the absolute velocity v2 at the outlet of the vane, right? v2 makes an angle beta with the tangent to the impeller at the outlet. Further, v2 can be resolved as a vw2 component and vf2 component at the outlet. Okay. Second assumption is there is no loss of energy in the impeller due to friction and due to eddy formation. That is ideal assumption number 2. No loss of energy due to friction. Assumption 3, no energy loss due to shock at the entry of the vane. Assumption 4, the uniform velocity distribution in the passages between the two adjacent vanes, right? The velocity profile is taken to be uniform. Figure shows a portion of an impeller of a centrifugal pump with one vane and the velocity triangles as I described at the inlet and outlet tips of the vane. Let capital D1 represent the diameter of the impeller at the inlet. So therefore R1 is equal to the radius at inlet, that is equal to d1 by 2. Okay, inlet is represented by subscript 1 and outlet is represented by subscript 2. Capital N represents the speed of the impeller in rpm, and suppose omega represents the angular velocity of rotation, that is given by formula 2 pi n by 60. u1 is the tangential velocity of the impeller vane at inlet, right? That can be calculated by a formula pi t1 n by 60. It is nothing but a formula of omega into r1, right? d2 suppose represents the diameter of the impeller at the outlet, so radius r2 equal to d2 upon 2. Similarly, u2, small u2 represents say tangential velocity of impeller at outlet, so that is equal to omega into r2, that is also equal to pi d2n by 60. Suppose v1 represents the usually absolute velocity of water at inlet, then vw1 is the velocity of whirl at inlet, vr1 is the relative velocity of liquid at inlet, vf1 is the velocity of flow at inlet, say alpha is the angle made by absolute velocity v1 at inlet with the direction of motion of vane. Now here it means with the tangent to the impeller. Say theta represents the angle made by relative velocity vr1 with the tangent. Similarly, the terms v2, vw2, vr2, vf2, beta and phi are the corresponding values at the outlet of the vane. Now, as the liquid passes through the impeller, the velocity of whirl changes and there is a change of momentum of the liquid. This change of momentum is nothing but change of angular momentum of the liquid as it passes through the impeller. So therefore, the torque acting on the impeller or the torque acted by the impeller is given by a formula, it is equal to rate of change of momentum of the liquid, right? That is nothing but rate of change of angular momentum of the liquid. Okay, now let us write the angular momentum of liquid at inlet per unit time per second, that is equal to linear momentum of liquid at inlet multiplied by radius at the inlet. Linear momentum is product of mass flow rate, so this is m dot mass flow rate into whirl velocity at inlet, VW1, right? Why whirl velocity? Because whirl velocity is the tangential component of V1. So m dot into VW1 gives you linear momentum at inlet into radius at inlet R1, right? Here mass flow rate is given by formula rho a V1, because it is the case of a series of vanes, and since VW1 is 0, so the angular momentum at inlet is equal to 0. Similarly, angular momentum per second at outlet is equal to linear momentum at outlet multiplied by radius at the outlet. So that is equal to m mass flow rate into VW2 into R2. Okay. So thus we write torque exerted by impeller on the water as it is equal to final angular momentum minus initial angular momentum of the liquid. Please note, this is a formula for torque exerted by the impeller onto the liquid. So the formula is torque T equal to final angular momentum minus initial angular momentum of the liquid. If you write a formula for a torque exerted by the liquid onto the rotor, as we have written in derivation of a Francis turbine, then the formula is torque equal to initial angular momentum minus final angular momentum. Okay? That is the case from the liquid onto the rotor. Here it is a case of from the impeller onto the liquid. So this is equal to m VW2 R2 minus 0. So finally torque is equal to m into VW2 R2. Unit will be Newton meter. Therefore, work done per second by the impeller onto the water is equal given by the torque exerted into angular speed. So that is equal to torque into omega. So this is equal to m into VW2 R2 into omega. R2 into omega can be written as U2. So therefore, work done per second by the impeller onto the liquid is equal to W dot is equal to m VW to U2. Its unit will be watt Newton meter per second. Let us call this as equation number 1. Thus we write the work done per second per unit weight of the liquid as W1 is equal to work done per second W dot divided by the weight of the liquid per second is m dot into G, right? M dot cancels out. Formula is VW to U2 upon G. Unit is Newton meter per Newton. Okay. Here the equation number 1 has been developed assuming that at the inlet the flow at inlet is purely radial. So the assumption is VW1 is equal to 0. But if the flow at inlet is not radial, then the formula of a work done by impeller per second is m dot into bracket VW2 U2 minus VW1 Q1. This would be the formula. Or the work done by the impeller per unit weight of the liquid is equal to 1 by G VW2 U2 minus bracket again VW1 U1 within the bracket. Okay. So this rate of work done is divided by m dot into G. So m dot cancels. So 1 by G VW2 U2 minus VW1 U1 bracket complete. Let us call this as equation number 2. The above equation number 2, that is the rate of work done per unit weight of the liquid W1 quantity, is also known as Euler momentum equation for the centrifugal pump. Okay, here the term 1 by G in bracket VW2 U2 minus VW1 U1 bracket complete. This term is referred as Euler's head, okay, represented by He, or it is also called as theoretical head, imparted by the impeller onto the liquid. Why it is called Euler's head? Because the term has a unit of meter and it represents the pressure head imparted by the centrifugal pump impeller onto the liquid, that is being handled by the pump. Okay. Note the equation number 1, that is VW2U2 upon G, stipulates that for delivering the liquid at high heads, the peripheral velocity U2 must be high enough, and also the vector VW2 must be large enough so as to provide adequate whirl to the liquid, right? The equation number 1 is this: W dot is equal to m dot into VW2 U2, right? So if you want to deliver a high head to the liquid, so your peripheral velocity U2 must be high, and also your whirl velocity VW2 must be large. Now the increase in U2 can be obtained by increasing the impeller diameter, and also it can be obtained by increasing the speed of rotation of the impeller. Okay. While the whirl component VW2, it can be augmented by providing adequate number of vanes of a suitable size and shape onto the impeller, right? Now from the outlet velocity triangle, referring to the from outlet velocity triangle, we have VR2 square here. VR2 square is equal to VF2 square plus bracket this term, that is U2 minus VW2 bracket square, right, from this triangle on the right hand side. VR2 square is equal to VF2 square plus bracket U2 minus VW2 bracket square. Okay. So from this you can write what is VF2. So VF2 square is equal to VR2 square minus bracket U2 minus VW2 bracket square. Let us call this as equation number 1. Okay. Also from the same OVT you can write VF2 square also equal to V2 square minus VW2 square. So here VF2 square can also be equal to V2 square minus VW2 square from the Pythagoras theorem. Okay. Let us call this as equation number 2. So comparing these two, we can write V2 square minus VF2 square as equal to the VF2 square, and substitute for VF2 as VR2 square minus bracket U2 minus VW2 bracket square. Then expand the bracket, that is equal to VR2 square minus bracket U2 square plus VW2 square minus 2 times U2 VW2 bracket complete. This is also equal to VR2 square multiplying inside the bracket with minus sign, and simplifying you get U2 into VW2 is equal to 1 by 2 bracket V2 square plus U2 square minus VR2 square bracket complete. Okay, this is the term. Similarly, from the IVT, if VW1 is not equal to 0, if a VW1 term is not equal to 0, from the IVT triangle you can get a formula U1 VW1 is equal to 1 by 2 bracket of V1 square plus U1 square minus VR1 square, right? Substituting this, both of these two expression into equation number 2 and simplifying, we get work done per second per unit weight of the liquid, that is Euler's head HE, as equal to capital V2 square minus capital V1 square by 2G plus U2 square minus U1 square by 2G plus VR1 square minus VR2 square by 2G. Okay. Substituting this expression and simplifying, you get a equation number 3. This above equation number 3 is known as fundamental equation of a centrifugal pump. It has 3 terms. First term, V2 square minus V1 square by 2G, and it represents the increase in kinetic energy of the liquid as it flows inside the impeller from inner periphery to outer periphery. This term is also represents the dynamic head exerted by the impeller onto the liquid, or it represents increase in kinetic energy of the liquid that corresponds to absolute velocities. The second term, small u2 square minus u1 square by 2g, represents an increase in static pressure of the liquid as the liquid flows from inner periphery to outer periphery of the impeller. The third term, Vr1 square minus Vr2 square by 2g, it indicates the change in kinetic energy due to retardation of flow relative to the impeller. Okay. It represents the change in kinetic energy due to retardation of the flow relative to the impeller surface, and this term therefore represents the conversion of kinetic energy, which is corresponds to the relative velocity, the conversion of this kinetic energy into the pressure within the impeller itself. Okay. So the retardation is taking place with respect to the impeller surface in terms of relative velocity, and it is ultimately converted to increase in the pressure in the impeller itself. Okay, thank you.